This video talks about operations on signals and then discusses some common signals. Here's a page that illustrates a few of the common operations on signals. Note that in all of these examples, we are applying operations to the independent variable. These are all discrete time signal examples, and we'll move more and more to discrete time examples. Here, the independent variable n is discrete in the sense that it takes on integer values and is not defined in between those integer values. So there is no value for x of 1/2, for example. Only x of 0, 1, 2, 3, and so on. You can put negative numbers in, that's fine. They just all have to be integers. And so here's an example signal. It's finite length. It has 6 values going from 0 to 5. We would call that maybe the support set of this signal because it's 0 everywhere else, including where it's not shown on this number line. But I've also highlighted, just for reference so that we can see this a little bit easier, I've colored the sample of the signal at time 0 blue, just so that we can keep track of it a little bit better as we look at some of these operations. The first operation that I want to look at is a simple time delay. So we've taken the independent variable and subtracted 4. That gives us a time shift of 4 samples to the right. We still have the same, the samples are still ordered the same as they were before, they're just all uniformly shifted to the right. When you add 4 to the independent variable, that shifts to the left. We might call that an advance. If this is a delay, this would be a time advance. And here we've shifted to the left by 4 samples. A time reversal is where we change the sign on the independent variable. And now you can see that the signal samples that were lined up to the right of the 0 point are now lined up in reverse order to the left of the 0 point. So it's a reflection about time 0. Here we have a combination of those kinds of things taking place. You could visualize this maybe first as performing a time advance by 4 samples. So it looks like this. So we advance by 4, and then we do a time reversal. Put this minus n in. And so hopefully you can see that if we took this advance by 4 waveform and did a reversal, it would look like what we show here. Notice that the value that's at time 0 is still at time 0 when we do a time reversal. And then here's another example where we have done a delay by 4. So this example here. And then we time reverse that. So that produces this example here. So we've got a delay and then a time reversal. Those are the operations that I want you to keep track of for right now. Delays, advances, and reversals. And now let's talk about some common signals. The first of these are impulse functions. If you've had a class already on continuous time signals and systems, then you're familiar with the delta function. We're going to call that the Dirac delta function in this class to keep it straight and separate from the discrete time version, which is called the Kronecker delta function. Or again, when there's no chance for confusion, we'll just refer to these as delta functions. But the thing that you remember about this oddball function called the Dirac delta is that it has infinite amplitude at one point and is 0 everywhere else. It integrates to 1, so it has unit area. And then this is actually, if you look at this closely, this is the convolution between a signal x of t and delta of t. And so when you convolve with a delta function, you reproduce the signal. That's maybe one way to interpret what's going on here. Another way to interpret what's going on here is that this delta function turns on at time t, or when tau is equal to t. So tau, think of t as being fixed here, like you do in convolution, and tau is our variable. So when tau is equal to t, this delta function turns on. And the only value, and since we're multiplying by x of tau, the only value in this infinite function x of tau that matters, the only value is when when tau is equal to t, and so that comes through the integral. The Kronecker delta function is a well-defined sequence of numbers. We don't have to worry about infinite values or things like that. It's a function that is 0 everywhere for all integers except for the integer 0, where it turns on and takes the value 1. You can see that defined here mathematically. Like the Dirac delta function, the analog of integration in discrete time is summation. So if we sum the Kronecker delta function, it sums to 1. You can see that by looking at the values of the signal here. We're basically adding up an infinite number of zeros, and then we have one value that is 1. And so that's why we get a summation of 1. Similarly, right here, this is, if you look at this closely, it has a similar form to this convolution integral on the left. This is a convolution sum. And what this is basically telling us is that when you convolve a sequence or a signal with a delta function, a Kronecker delta function, you reproduce that same sequence that you started with. So those are a few things about delta functions. One other very important property of delta functions, which is true for both the Dirac and the Kronecker, is this property I'm calling the sifting property. Let's see what this means. I'll talk about this example, using this example here at the bottom. So what I've done here is depicted a generic signal sequence x of n, a discrete time signal. I've shown that the samples of that signal using a stem plot, as you see here. I'm also showing you a delayed Kronecker delta function. This one, in this case, is delayed by 20 samples. So instead of the value 1 occurring at time 0, it now occurs over here at time 20, or index 20. Now, the sifting property is applied, or may be applied, in either direction whenever you have a waveform being multiplied by a delta function. So that's what's being implied here on the left. We've got a signal x of n being multiplied by a delta function, a delayed delta function, in this case, generically delayed by k samples. When that product occurs, which is what we see here, think of multiplying this sequence by this delta sequence. What will the product look like? Well, because most of the samples in the delta sequence are 0, most of the samples in the product will be 0 as well. In fact, there will only be one non-zero sample in that product, and that occurs at sample index number 20. Now, because we're multiplying these things together, remember the delta function has amplitude 1, and so the value of the product will be whatever the signal sample happens to be at that time when the delta function turns on. So this is called sifting. We think of the delta, this point at which the delta function turns on, as sifting out only one of the values of the sequence. From among all the values in the sequence, this sifts out just one. And so what we can do is anytime we see a function, one function multiplying a delta function, the only value in the delta function that matters is the value at the time when the delta function turns on. And so we're able to replace the n independent variable with k. That's called the sifting property. And you can use it in either direction. If you see this appearing somewhere in an equation, you can replace it with that. Or if you see this appearing in an equation, you can replace it with that. And keep in mind the picture to go along with the math. Here's the convolution property proven for the Kronecker delta function. Stated mathematically, if you convolve a signal with a delayed delta function, you'll get a delayed copy of the signal, where the amount of delay imposed on the signal is the amount of delay in the delta function. So let's just expand this out and try and review some of our memory of convolution. So here we have convolution written out sort of symbolically. And the way we evaluate convolution is we write down a summation, and then we replace in one of these signals, and I'm going to do this in the x signal, I'll replace the independent variable with I, which is the index of summation. And then in the delta n minus k, I'll replace the n variable with n minus I. Of course, we could have done it the other way around. We could have put n minus I inside x and I inside delta, but we're going to do it like this. So this is essentially writing down formally the definition of convolution in discrete time. The second step here is nothing more than just a slight rearrangement of the argument of the delta function so that we can pull out this I variable, because that's the variable. K and n here are just fixed numbers. We're summing on I. Now we see that we have a signal x multiplied by a delta function. Now we can apply the sifting property, which says that we can replace the independent variable in the signal x with the time at which the delta function turns on, which is n minus k. And so that's what's done between these two steps. I've replaced I with n minus k. That's called the sifting property. Now you see that x no longer depends on I, which is the index of summation. And so we can pull x out of the sum. So now I have x times the sum of delta functions. And remember now that the delta function sums to 1. So this summation goes away. It has a value of 1, and we're just left with x of n minus k. So if we go back and review where we started with convolving x with a delayed delta function, and the answer is that we get a delayed version of x. That's called the convolution property of the Kronecker delta function. That's something you can commit to memory. It's the same property that you saw in continuous time when you convolve with the Dirac delta function. It's the same thing, just written down in discrete time. So that's something that you should commit to memory. Same with the sifting property. That should be committed to memory. Here's just a simple example of the convolution property being applied. Here I have a signal x which turns on at time 0. It has finite support. It looks like it has 4 non-zero samples in the signal. And here is a delta function that turns on at time 20. If I convolve this signal with this delta function, I will get a delayed version of my original signal. So this doesn't show all of the intermediate steps in convolution with flipping and sliding and so on. This is just the answer, and we can use this now because we proved the general case on the previous slide. So whenever we encounter a signal convolved with a delta function, we know what it does. It just delays that signal. Another thing that delta functions are useful for is representing signals. Let's go back to the idea and remember that if we have a delta function that turns on at time k, I'm sorry, in this case the delta function turns on at time n. K is the independent variable. N is a fixed number. It could be 20, it could be 1,000, 1,000,000, whatever. That's just a number. This delta function turns on at time n and is 0 everywhere else. Now when you see a summation like this with no limits specified, we default to assuming that the limits are that we're summing from minus infinity to positive infinity. So no matter the value of n, this sum includes that value. So this sum is adding up all of the infinite number of zeros in this delta sequence, and it is also adding up that one value of 1, and so the sum is 1. This is useful to develop a representation for signals. So let's suppose x is an arbitrary signal. Let's multiply both sides of this equation by x. So here we're multiplying x by 1 on the left. Of course, that gives us x back. And then here we're multiplying by the sum of this delta function, which again has the value of 1. But what we'll do now is we can bring x of n inside the sum, because it's not a function of k, so we can freely bring it in. And now we see that we have x times a delta function. Anytime you see x times a delta function, one of the things that you will at least want to think about is the application of the sifting property, which if we apply here, we can replace n as the independent variable with k. This is using the sifting property in reverse. Here we have, well, it's the reverse of the way we've used it before. But now we can see that this has the appearance, the natural appearance of convolution, because we have x of k and delta n minus k sum on k. That looks like convolution, which it is. And so we have this representation formula. X of n can be written as, you could think of this as a convolution, but now we're sort of thinking of this differently. We're thinking of this as a representation of a signal x of n, as the infinite summation of weighted delta functions. That's a new way to think about signals, and they're being represented by delta functions. Here's an example of that. I can't fit on one page all of these delayed delta functions, but and so I've represented just a few, and I'm using ... here to cause us to think about the fact that there are delta functions not displayed here. But what I've displayed here on the top number line is delta at n plus 2, that turns on at time -2, times the signal at time -2, which happens to be negative in this case. On the next number line, I have delta at n plus 1, which turns on at time -1, times the signal at time n minus 1. And so on. Here I am at time 0, time 1, 2, and so on. And if you add these all together, we're at any time we're adding a non-zero value to an infinite number of zeros, and so we just get that non-zero value. So here is the signal x of n. It's some kind of a sinusoidal type signal. But we see here that we can represent this signal as an infinite sum of delayed and scaled delta functions. That's the power of this representation, and we'll use this later on to develop an important property of linear time invariant systems. So once again, another use for delta functions is to represent arbitrary signals by adding up delayed and scaled copies of those delta functions. Let's take a look at another example or another use for delta functions. In this case, if we take delta functions and add together an infinite number of them, but instead of being delayed by one sample, they're delayed by n samples, we create this periodic train of impulses. I'll show you an example of what that looks like on the next slide. But if we convolve that periodic train of impulses with an arbitrary signal, g, a basic pulse, we'll say g of n, then what we do is, if we substitute this this train of impulses in, that's like convolving the basic pulse with each of the delayed deltas in the impulse train, and so we basically get we reproduce a copy of this basic pulse at each of the locations of the delta functions. That's the convolution property of delta functions, illustrated here. And so what we get, what xn turns into, is what we could call a periodic pulse train. P is a periodic train of impulses. X is a periodic train of pulses, G. We get replicas of G reproduced all the way across the number line. Let's take a look at an example graphically. So here's our basic pulse, G. It's defined by these 4 non-zero samples. And then here's our impulse train. In this case, capital N is equal to 5, and so we have every fifth sample is a delta that turns on. These are, remember, these are being produced by adding together isolated delta functions. And when we add all those together, we get a periodic train of those. So every fifth sample turns on, and it's 0 in between. And then if you convolve this basic pulse with this train of impulses, we can construct a periodic signal whose every period is basically a duplicate or a copy or replica of this basic pulse. And so we can construct periodic signals by convolving a basic pulse, a non-periodic pulse, with a periodic train of impulses. So in review, here's a summary of the properties of both the Dirac and the Kronecker delta function. First, we have the sifting property, both for continuous time and discrete time. We have the convolution properties represented here. We have periodic impulse trains, and then periodic pulse trains constructed by convolving a basic pulse with a periodic train of impulses. So these are all things that we should remember about delta functions. The next signal that I want to talk about is the step function. Again, you're probably familiar with the continuous time unit step function. That is 0 before time 0 and 1 after time 0. It's possible to define that as the integral of the delta function, or in reverse, defining the delta function as the integral, or I'm sorry, the derivative of the step function. If we go over to discrete time, the discrete time unit step function is 0 before time 0 and 1 from time 0 onwards. This is that piecewise definition stated mathematically, similar to the Kronecker delta and the unit step in continuous time. I'm sorry, the Dirac delta in continuous time. We have a relation between the unit step in discrete time and the Kronecker delta being the accumulation or the summation of the Kronecker delta. Similarly, we could write that the Kronecker delta is a time difference. It's a difference between the unit step and the unit step delayed by one sample. It might be useful to see that illustrated. Again, the property that we're trying to prove here is that the Kronecker delta is the unit step subtracted from the unit step delayed by one sample. So let's just draw this. So this is 0, minus 1, minus 2, minus 3. The unit step turns on here at time 0, 1, 2, 3, and so on. So this is u of n. If we draw also u of n minus 1, that will be 0, 0, 0, 0 at time 0, and at 1 it turns on because we've delayed by one sample, and so on. Now if we subtract these things, over here at negative times I have 0 minus 0, so that gives me 0. At time 0 I have 1 minus 0, so that's 1. And then at positive times I have 1 minus 1, which is 0. 1 minus 1, which is 0. At time 2 and 3, and so on. So this is delta n. And that's a quick, I don't know if you'd call it proof, but a graphical proof that this property is true. You could think of time differences in discrete time as being analogous to the derivative property in continuous time. In fact, if we write the derivative property in continuous time, let's see, we have delta of t equal to the limit, as say h goes to 0, of u of t minus u of t minus h divided by h. That's the formal definition of the derivative. And we see that if we just simply let h equal to 1 and we don't take the limit, we stop short of taking the limit, then this gives us something that's analogous to u of t minus u of t minus 1. So it's like an approximation to the derivative. You really can't take the derivative in discrete time, although we will come very close to doing that later in the course when we talk about differentiating filters. But for right now, just keep in mind that integrals in continuous time become sums in discrete time, and derivatives in continuous time turn into these delayed differences in discrete time. Some other commonly encountered signals in this course, in our discrete time signal processing class, are the aperiodic sinc function shown here at the top. It has this same form as a sinc function you're probably familiar with, but it's only defined at integers. And at time 0, it takes on the value 2b in this case. I've drawn the picture below for the case where b is equal to 1/10, and we note that the zero crossings occur at multiples of 1 over 2 times b. So if you plug in the values, that turns out to be 5. So the important thing about sinc functions to remember is that they have periodically repeating zero crossings. Being able to find those zero crossings is an important skill that you should have. It may be based on the value of b. If 1 over 2b does not turn out to be a integer, then we would say that this aperiodic sinc function, the zero crossings do not occur in the sequence. That's very possible. The other kind of a sinc function, which may be new in this course, you may not have seen this before, is a periodic sinc function, where we have a sine function in both the numerator and in the denominator. And in this case, the period of this periodic sinc function is 1. You can see that it repeats here every integer. And at time 0, or at the integers, it takes on the value n, which comes from this the argument of the sinc function in the numerator. So those are two functions that we will encounter later in this course. Another very important example are complex exponential signals. In this case, we're seeing a causal complex exponential signal because we have this a to the n being multiplied by u of n, which is our basic causal signal. Anything times u of n will automatically be causal. Now, if the value of a, so think of a as being a complex number, and here I've drawn the complex plane with the unit circle drawn in this dark blue color. If the value of a, or the magnitude of a, is less than 1, then we'll have a decaying exponential. If the magnitude of a is equal to 1, then a appears somewhere on the unit circle, and we'll have a constant envelope exponential signal. If the magnitude of a is greater than 1, then we'll have an exploding signal as you move to the right. And I'm just sort of representing that here again on this slide with the zoomed in portion of the complex plane shown. So here again you see the interior of the unit circle itself being this thick green or blue line, and then the exterior of the unit circle. Now, if the radius of a, or the magnitude of a, think of that as being the radius of a circle on which the value of a lies. So if that radius is small, then we have a quick decay to the envelope. As the radius gets larger, the decay of the envelope of that signal slows down. And then when you actually have a radius of 1, you have a constant envelope signal with neither decay nor growth. But then as that radius becomes larger than 1, you begin to get growth in the waveform. And as it becomes larger and larger, the rate of exponential growth increases. So this is true in discrete time as it is in continuous time. Another important concept is the frequency of a complex exponential signal. And this chart here provides a summary of the idea. Note that I am drawing here discrete time complex exponential signals over the range of the independent variable from 0 to 10. But I'm connecting the samples, rather than drawing these as a stem plot, I'm connecting the samples with lines. So the blue part is the real part of the exponential signal, and the red line is the imaginary part of the exponential signal. And in this case, the magnitude r, or the radius of the exponential, is 1. I've selected 10 points around the unit circle to be the phases for the complex exponential. So what we're seeing here is increasing. We're seeing plots as the frequency increases. So if the frequency is 0, then of course we get a constant. That would be considered the equivalent of DC, direct current in continuous time, 0 frequency. But here we have a frequency of 1/10, so that as in the course of 10 samples, we move through a single period of the complex exponential. When we go to 2/10, over that same time period, over 10 samples, we go through 2 periods of the complex exponential signal, then 3/10, 3 periods, and so on, all the way until we get over here to what I'm going to say is the highest frequency. This frequency would be 1/2. Here's a frequency of 1/10, 2/10, 3/10, 4/10, 5/10. That's 1/2. And notice that the real part of the signal is toggling between +1 and -1, +1 and -1. And the imaginary part, which is the sine component, is just taking on the value of all zeros. That's the highest frequency signal that you can have in discrete time. There is no higher frequency signal than that. And so as we continue around the unit circle, going to 6/10, 7/10, 8/10, and 9/10, or thinking about negative frequencies, -1/10, -2/10, and so on. Even though maybe these frequencies have higher numeric value, 6/10 is greater than 5/10. 7/10 is greater than 5/10. Even though the value of the frequency is higher than that so-called highest frequency, the sequence itself has lower frequency. In fact, if you look and compare the waveform, in fact, it's easiest if we look over here. If you look at the waveform for 1/10 and 9/10, the real part is exactly the same. The imaginary part has just been flipped upside down. Instead of positive sign, it's negative sign. And so 9/10, even though it's a higher numeric value than 1/2, has lower frequency than 1/2. So these are low frequency signals. This is high frequency signal over here. On the left side of the unit circle, you get high frequencies. On the right side, near 0, you get low frequencies. The other thing that we come to understand by looking at this chart is that the frequency -1/10 gives you the same sequence as the frequency +9/10, and so on. In fact, the frequency 0 is the same as the frequency 1. And if we circle around again, we'd count 2 and 3 and 4 and so on. So all integers have the same frequency as 0. And this leads to the concept of frequency aliasing, which we'll talk about later on. This chart simply summarizes those ideas that we just talked about. High frequencies are frequencies near plus 1/2 or minus 1/2. Low frequencies are near 0. Another useful tool that we will encounter when we talk about systems are polynomials and ratios of polynomials, also known as rational functions. So here, the polynomials, unlike many that we've seen in the past, the polynomials generally will be z will be our independent variable, and the polynomial will be expanded in terms of negative powers of z, as you see here. So we'll have z to the 0, z to the -1, z to the -2, and so on, up to a polynomial of order m. This is written out in polynomial form, but we could also find the roots of the polynomial and write it in product form in terms of the roots, or the zeros, as you see here. For a rational function, we have a polynomial in the numerator and a polynomial in the denominator. They could have different orders. In this case, we have a polynomial of order m in the numerator and a polynomial of order n in the denominator. If we write it out in factored form, we can identify the so-called poles and zeros. P are the poles and z are the zeros of this rational function.